Le Chatelier's principle defines how this reaction defines distress. For example, in order to shift the reaction to the right, you can add one of the reactant.
We are going to be talking about the concentration, increasing or decreasing the concentration of something. Here we have hydrogen and oxygen on the reactant side and water on the product side. If we increase the concentration of one of the reactants, it will shift away from it and increase the products. If we decrease one of the reactants, it'll shift towards the products, making it greater.
This is an example of the formation of water. On the reactant side, we have two H2 molecules and one O2 molecule. On the product side, we have one H2O molecule and heat. If you add heat to the system, here's our heat, it will go in the exothermic direction, which is towards the reactants. The same system, and we removed some of our heat, it would go in the
Increasing or decreasing the pressure on a system is very important to the Le Chatelier's principle. If you increase the pressure, you're going to shift to the side with less moles. If you decrease the pressure, you're going to shift to the side with the more moles. For example, if you increase the pressure and you have 3 moles on one side and you have 2 moles on the other, since you increase the pressure, you're going to go to the side with less moles, which would be 2. So you're going to go from the side with 3 moles to the side with 2 moles. And then it's going to shift to the less moles. And if you decrease the pressure, you're going to go to the side with more moles. So you're going to shift from the side with 2 moles to the side with 3 moles, and which would increase that side. Now we are going to talk about adding catalysts, solids, and liquids. There are only 2 things that can, 2 phases of matter that affect Le Chatelier's principle: either gases or aqueous solutions. If you add a solid or liquid, it does not affect the reaction. I mean the shifting of the reaction. It does not count as part of Le Chatelier's principle.
The direction a reaction shifts is dependent on the reaction quotient and the reaction constant. For example, let's say we have the equation AA plus BB yields CC plus DD. The reaction constant, K, is calculated using the formula the concentration of C to the C power times the concentration of D to the D power divided by the concentration of A to the A power times the concentration of B to the B power, and in this case the concentrations are at equilibrium. The reaction quotient, also known as Q, is calculated the same way as you calculate K, but the concentrations that you input into the equation are at a given time. The relationship between Q and K determines many things within the reaction. For instance, if the Q value is greater than the K value, the reaction will shift to the left, meaning that it will tend to produce more of the reactant. If the Q value is less than the K value, the reaction will shift to the right, producing more products. And if the Q value equals the K value, the reaction is already at equilibrium. In another reaction, let's say we have A yields B. You will set up your K equation to be the concentration of B over the concentration of A, which we will set to equal 1 for simplicity's sake. Now, let's say you get this statement. At the start of the reaction, 4 moles per liter of B is mixed with 2 moles per liter of A. You'll set up your Q equation by, again, the concentration of B over the concentration of A, but this time plugging in the given values, which will be 4 moles per liter over 2 moles per liter, and you will divide to get 2. What this means in our other example, where Q was greater than K, since 2 is greater than 1, is that it will shift left, producing more of A.